Good morning to all of you. I am Kshitij, and in today's lecture we are going to do some numerical problems from the chapter Units and Measurement. Okay, so before we start, I would like to request you all to do subscribe to our YouTube channel, share the videos you find interesting there, as well as click on the bell icon to receive the future notifications. Okay, so we will start with numericals on significant figures. We will start with numericals on number of significant figures. So we are given 6 subparts of the question and we need to find the number of significant figures in each of them. So part A we will start. So part A is 0.007 meter square and we need to find the number of significant figures. So first thing to observe here is that number is less than 1. So if a number is less than 1, so all the zeros to the right of decimal place before a non-zero digit are considered non-significant. So here we are having two zeros before first non-zero digit comes. So these first two zeros will be considered non-significant. So here in 0.007, two zeros after decimal point will not be significant. So we will be having only one significant figure, that is 7. So number of significant figures will be 1. Okay, so now we will move to part V. We are having 2.64 into 10 to power 24 kg. Okay, so now comes rule number 2. So while calculating the number of significant figures, we have to ignore the powers of 10. We have to ignore the powers of 10. So 10 to power 24 will not be considered in taking the number of significant figures. So we are left with 2.64. So all the three digits are non-zero and therefore they will be considered as significant figure. So 2.64, 2 is significant, 6 is significant and 4 is also significant. So number of the significant figures will be equal to 3. Okay, now move to part C. We are having 0.2370 gram per centimeter cube. Okay, so to the right of the decimal place we are having a 0, but that 0 is not leading but rather it is trailing 0. So whenever we are having a trailing 0, we will consider it as significant figure. Okay, so 0 is at the end. Okay, trailing zeros are considered significant. So we will have 4 significant figures, 2, 3, 7, 0. So we will have 4 significant figures in this case. Now we will move to part D. In part D we are having 6.320 joule. Okay, so here it is a decimal number, first observation, and second observation is that 0 is not leading but 0 is a trailing 0. So trailing 0 will be considered as significant figure. Okay, so we will again have 4 significant figures, 6, 3, 2, 0. So all 4 are significant. We will have 4 significant figures. Now we will move to part E. In part E we are having 6.032 Newton per meter square. Okay, so we are having 0 here between two non-zeros. So here comes another rule. The rule is that any 0 between two non-zero is considered as significant figure. Okay, so we will have 4 significant figure again, 6 as first significant figure, 0, then 3 and then 2. We will have 4 significant figures. And we will move to last part of the question, numerical problem. We have to consider 0.0006032 and we need to consider the number of significant figures. So there are 3 zeros to the left of 6 and 1 zero to the right of 6. 3 zeros to the left of 6 and 1 zero to the right of 6. So 3 zeros to the left of 6 are not significant, as we have already told in the part A, but 0 to the right of 6 between 6 and 3 will be considered as significant figure. Why? It is lying between two non-zeros, so it will be significant. So again we will have 4 significant figures. Okay, so now we will move to next numerical problem. Okay, so now numerical problem 2, we are having a physical quantity P that is related to 4 observables A, B, C, D as per a given formula, and then we are given the percentage errors in measurement of A, B, C and D. Okay, and we need to find the percentage error in the quantity P. Okay, so how are we going to calculate the percentage error in the quantity P? We are going to calculate the percentage error in the quantity P by using a concept called as propagation of errors. Okay, so we have studied that how error propagate. We have already covered the topic in another video. Please go through that. That is a video on units and measurement. We have covered the topic there. Okay, so we are knowing that the propagation of errors, 5 cases are there: addition, subtraction, multiplication, division and exponent. So we will use that concept here. Okay, and we will arrive at the formula. Relative error in P will be 3 into relative error in A plus 2 into relative error in B, and since in the denominator we are having under root, so plus 1 by 2 relative error in C and plus 1 by 2 relative error in D. So we will come at the formula this: delta P by P is equal to 3 into delta A by A plus 2 into delta B by B plus 1 upon 2 delta C by C plus 1 upon 2 delta D by D. From the formula be calculated by using the concepts of propagation of error. Okay, so now we are given the percentage error, we are not given the relative error. So what will we do now? We will multiply both the sides LHS and RHS by 100. Why are we doing this? To change the relative error into percentage error. Okay, so we will multiply both the LHS left hand side and right hand side by 100. So we will get this. Okay, so now we have rearranged it. Okay, and now we are given the percentage error in A, percentage error in B, percentage error in C and percentage error in D. We are given percentage error in A, percentage error in B, percentage error in C, percentage error in D. Percentage error in A is 1%, percentage error in B is 3%, percentage error in C is 4% and percentage error in D is 2%. We are putting it into the formula and we are calculating percentage error in P as 13%. Okay, now some value was given of P. So we need to round off that to 2 significant figures. Why 2 significant figure? Reason is that percentage error is 13%, that will come to 2 significant figures. So we have to round off the result to 3.8. We will move to numerical problem number 3. We will move to numerical problem number 3. We are given 3 equations in simple harmonic motion. Okay, and they are related by the displacement. Y is displacement, A is the maximum displacement, T is time and B is the speed of the particle. And we need to tell out of the 4 given equations in the simple harmonic motions which one are correct and which one are incorrect. Okay, so how are we going to analyze this question? I will give you a clue here, I will give you a trick here. Trick is that we are using the trigonometric function in all the 4 equations, and trigonometric functions operates on angles, whether the angle is in degree, angle is in radian, angle is in minutes or angle is in second, but all the trigonometric functions operates on angle, and angle is a dimensionless quantity. Angle is a supplementary unit and it is a dimensionless quantity. So we need to take this part. Are you getting? We need to take this part and we need to check whether this part is dimensionless or this part is not dimensionless. Okay, so on the basis of this we will be deciding whether the given equations are correct or given which one of these is correct and which one of these are incorrect. Okay, so after the sign we will use the angle part and we need to prove that the part is dimensionless. the red lined part, I mean to say. So we will calculate the dimension of 2 pi t by t, we will calculate dimension of vt, we will calculate dimension of t by a, and we will calculate dimension of 2 pi t by t, and we need to see which is dimensionless and which is having the dimension. Okay, so this part will become dimensionless, and we are having a by t and a root 2. Okay, correspondingly, after ignoring the trigonometric part. Okay, so the dimensions of a and y are same. So we will check the dimensions of the angle part. Okay, so how will we do? In the first part we are having 2 pi t by t. So dimension of t is m0 l0 t, and dimensions of capital T is also m0 l0 t. So it comes out to be dimensionless quantity. Okay, so we can have the quantity as dimensionless in trigonometric function. So it seems to be correct. It is correct. Now we will move to part 2. We are having Vt. The dimension of V is Lt minus 1 and dimension of T is T. So we are left with dimension L. That means M0 L T0. And it is not at all dimensionless. So there is some problem with the formula. This formula is incorrect. This formula is incorrect. Why? Angle cannot be having any dimension. So we will move to third part. We are having t by a. Okay, t is time and a is displacement. So we are putting in the formula, we are getting the dimension as L minus 1 t minus 1. So it is also incorrect. Why? Angle has to be dimensionless. Why we are having it in trigonometric? We are using it in trigonometric function. What we are using in trigonometric function? T by a. So t by a has to be dimensionless. Okay, we have already discussed t by a has to be dimensionless. So we are having fourth part 2 pi t by t. That is again dimensionless. Why? T is having dimension t and capital T is having dimension t. So that means we will have the 2 pi t by t comes dimensionless. So this is correct. So first is correct and fourth is correct, and these two, second and third, are incorrect. Okay, so we are moving to next numerical problem. Numerical problem number 4. Okay, so what is the fourth numerical problem? Actually, this numerical problem is that a boy forgot a formula. Actually, he don't know where to put C. C stands for speed of light in this formula. Actually, this formula is very famous formula derived by Sir Albert Einstein in theory of relativity. He told that how he discussed how mass of a particle is dependent on rest mass when a particle is moving with velocity comparable to speed of light. Okay, so we know that the m is equal to m0 upon some formula is there that will come in the next slide, but the boy forgot the formula. Okay, he forgot where to put C. Where to put C? I is speed of light. Where to put the speed of light? So we need to correct this formula. Okay, this formula is for relationship between mass and rest mass in terms of its velocity and speed of light. Okay, so we are having m is equal to m0 y 1 by b, 1 minus b square to power 1 by 2. It is incorrect formula. Okay, so we need to put C at the right place. So how are we going to do it? We know that dimension, by the principle of homogeneity, the dimensions of LHS has to be equal to dimension of RHS. Okay, we are having mass on the left hand side and mass on the right hand side. Already they are dimensionally correct. So we are having extra 1 minus b square to power 1 by 2 in the denominator. So how are we going to nullify the effect of 1 minus b square to power 1 by 2? How are we going to nullify the effect of 1 minus b square to power 1 by 2? We are going to nullify it by putting an extra c square in the denominator. And where are we going to put it? We are going to put it here. So the new formula will be m is equal to m0 divided by 1 minus v square by c square to whole power 1 by 2, or under root square root of 1 minus b square by c square. So what will happen? We know that v is the velocity of a particle and c is the speed of light. both are having the same dimensions. So b square and c square will cancel out each other, and in the denominator we will have dimensionless quantity. So already we know that m and m0 are having the same dimension, so formula becomes correct. So this formula is one of the most famous formula of the Albert Einstein to calculate the mass of the moving body moving with a velocity comparable to speed of light. Okay, it found its place in theory of relativity. Okay, so friends, that's all for today. See you soon in our next video. Thank you.